Good afternoon, everyone. This afternoon we're going to quickly look at the architecture and technology which we'll be focusing on for this semester in Software Engineering 2, as our design will be based on that. Now we will continue with this in the coming weeks, but more. So you can go and look at the objectives from this. But we will be focusing on an actual embedded system. So an embedded system, they tell us it's some combination of computer hardware or software, either fixed in capability or programmable, that is designed for a specific function or for a specific function within a larger system. Okay, so that is what we're aiming for. Now if we're talking about a embedded system, it might have inputs, it can be linked to other systems, and by linked it means that it can put data out, it can also receive data from other systems. Same with this, we can have user interface elements where it can display things for us, but it can also receive information back into our system, and then later on we can have outputs from this. Okay. So that is what we will be aiming towards, and it's merely an integration between your system intelligence, that's where the microcontroller or microprocessor is sitting, and then your sensors, which can be some sensor like temperature, humidity, gas or volume or such sensors, or it can also be actuators or buttons even. Okay, where do we see embedded systems? There's a basic list: security system, cruise control, heating or air conditioning, a thermostat, microwave oven, dishwasher, anti-skid braking system, traffic light controller, vending machine, fuel pump, handheld game controller, irrigation system. So that's a mention of just what can be done. It's really any place where we're trying to integrate electronics with some sensor, some mechanical sensor devices to do a bigger task for us. Okay. So where is this the correct tool to use? Now you'll see it's a correct tool to use when we actually have some intelligence in our system. And we have additional intelligence that we want to incorporate into it. If the complexity of a system is reduced when using a microcontroller, okay, the cost of the microcontroller is then less than discrete components. What is a discrete component? Like a component that cannot be? No, it's not like a discrete security component almost. When you initially started and you worked with gates, that is similar to a discrete component. You have just this basic IC and that can do certain things for you. Some of those things mentioned earlier on this previous list, if we had to build a security system, or even let's say traffic light controller, that can possibly be done with discrete components, small ICs. But the cost associated between using a microcontroller compared to a number of discrete components can be quite different. Okay. And then a variety of external components must be integrated into our system. Then it's still an option if there is communication with other devices which is required. I remember my first year of electronics, we had a project where we had to integrate a BCD encoder, and you had to develop a binary to BCD encoder as one project. You had to develop, put in all the gates to do it. That was still all the ICs. Then a later on project was used to put a BCD value to 7 segment. And then we were 4 people in a group. So each person had to do 1 digit. So you could display up to 1,000 values with yours because it can then count. So the last practical was meant to incorporate all of those things together. But it could have very been easily today been replaced just with a microcontroller, where everyone had to use discrete components. So when will you not use a microcontroller? Okay, if the system requires little or no intelligence, if it doesn't need to add additional behavior intelligence to it, if the system can be made easier and cheaper using our discrete components, your small ICs, then it can possibly be done quicker. If the microcontroller is undersized to the problem, okay, so if you might require something bigger than a microcontroller, okay? Meaning that you might need a bigger microcontroller, for example, a DSP, that can actually work faster to do certain tasks for us. If there's too much number crunching which is required, what does that mean? Number crunching. We would like to break someone's password with WAP encryption on the Wi-Fi port. You can use a microcontroller to do it, but it's going to be very slow. You can use bigger sensors and bigger devices to do it, and it can also do that for you. Okay. So there's just to mention quickly about the microcontroller and really the heart of the unit, which is a central processing unit, the actual CPU portion that interacts with your clock, some input ports, it has output ports, there's data memory and program memory. So that's really just a basic layout which you might see for a microcontroller, which it can have. Okay, then there's a quick mention about the clock inside the microcontroller. What does your CPU clock do? A modern CPU clock in a laptop can range between probably 1,000 megahertz to probably about 4,000 megahertz. That depends on the version. But what does that clock actually do? It gives you pulses per second. Actually, impulses are where it's going to do certain things for us. So it allows us to move data around the system, around the gates and around that CPU to make certain tasks and decisions for you. Okay. So the faster your clock, the faster that microcontroller is going to get through its logic, its required behavior. Okay. So then also microcontroller has ports, and these ports can be input ports or output ports. An input port can either take analog data or digital data. Okay. What is the difference between analog and digital data? Digital data is only going to be 0 or 1, 0 volt or 5 volt. Okay, or 3.3 volt in some cases. Okay, what is analog data? Is that an analog value, an analog signal? Yes. It could also be seen as, let's say, right. Still analog. Even this red sinus wave, which has now been shifted a bit, is that analog? Or is it digital? Why do you say it's digital? Digital is only going to be 0 or 1, or represent small bits for you. Okay. that portion of data, that wave, can be interpreted and can be read into analog values, into digital values. So what we're seeing is that this red sinus wave of ours, every small bit of it can be translated into a digital actual corresponding value. Okay. So, as I was saying to that, we have inputs and we have outputs on a microcontroller that can either take in binary, analog or digital data. Okay, even on your output, you can output analog values in terms of pulse width modulated data. Then it generates an analog wave through pulses, but it can also do digital values for you, 0 or 1, on or off. Okay. So here's a quick summary of the two. Analog is just coming back to that sinus wave we looked at now, and digital signals is going to be a combination of zeros and ones. Off, 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 on, whatever. Okay. Okay, so in a microcontroller you might have the ability also to store data, and that data is represented in terms of the actual address and the actual value what you are storing. Now we have different types of memory which can be used in terms of the address memory, program memory and so on, but we won't focus so much in terms of the actual memory address locations. We're going to more create the actual software applications for microcontroller. In essence, what it's saying to us is that for a specific address, which we might have on the microcontroller, we can store data, and this data can say, but this pin is going to be an output or an input. That's ultimately what we're designing to. Okay, so the microcontroller which we will be working or designing towards will be for a embedded Arduino system. We've played with Arduino before. No one. Why would we take something like an Arduino? Have you seen an Arduino? You look at a picture now of it. But Arduino is basically a small development board already with its microcontroller and a clock and all of that on top of it. And you can then use it from there on. It probably costs around 150 Rand already put together. Okay. Now, there's some information listed about it. It uses a simplified version of C++. And we can use our already existing C++ knowledge to write towards it. Okay, so we're going to look at using objects and classes and methods and so on in terms of this. It also contains a built-in programmer, which we can then either connect to, using USB from your computer or your laptop to the development board to write your code to it. Okay. Now it then uses a standard form factor, which other boards can be built on top of this to create bigger projects. Okay. So there is a quick overlay of the actual Arduino environment or board. Now that's Arduino Uno. It's one of the smaller ones. It's roughly about the size of your, just a bit bigger than your student card or bank card. Okay. Now, what you will see from this, it has a USB port over here. There's a power jack. There is a voltage regulator built on top of it. There's the crystal. And then we also have our reset buttons or reset pin. And then you can have your outputs in terms of 3.3 volt, 5 volt or grounds, and also a external voltage which can be applied and given into your Arduino. Okay, so that's mainly some of the components from it. if we continue, you'll see there's more on the other side of it. Now, then we have our analog pins over there. You have your microcontroller. Now, the microcontroller which they are using is a Atmel microcontroller. Okay. Then from this, we have also the ICSP pin, which can be used to program it. And then there is a power LED light to indicate that it's on. There's also two lights to indicate that there's serial communication happening. And then we have a reference voltage which can be given, and then you also have your digital output pins. Okay. So that's the main structure or components towards it. Now what you will see for these different Arduino boards, there's different size of these boards. The basic Arduino Uno operates at 5 volt. It has a 16 megahertz crystal. It can handle 14 digital outputs or inputs. Okay. And you can have 6 analog inputs. It can then also generate 6 pulse width modulated waves. There's one UART port, and it can use your USB to program it. Okay. Now the bigger brothers which we will have, for example, is the Arduino Megas, and there's a combination. There's also smaller ones which can be used. Okay. Now what you will see, for example, the Arduino Mega can handle 54 digital I/O pins. There's 16 analog inputs. So meaning that you can actually have 16 waves which you would like to read and take values from. Okay. Now what makes the Arduino nice, for example, is you can add components on top of each other. Okay. If you would like to put a system together to, for example, send a SMS or play some sound for you from a USB device, you can actually put it together. You can stack these devices on top of each other, and you can accomplish the same merely by just using your Arduino and other additional components or shields which you can then use to do this. Sure. Now what makes these shields nice is you can have external libraries which in most cases is pre-written. You can just use it in your program to help you to achieve certain tasks quicker in your actual design. Okay. So some of the shields, there's a few listed which we can get. There's actually a very long list of shields which is available. You'll see, for example, there is an Ethernet shield. The Arduino by itself does not have an Ethernet network jack. Okay? But by putting a shield on top of it, you can extend the actual functionality and you can make it available that it can use Ethernet. There's also some shields which is available for power over Ethernet. What is PoE? Makes it that you actually don't need to provide power to your Arduino, that the power which is then available through your Ethernet, your network cable, is then translated and basically gives this guy power. Okay. Then there's, for example, also like an MP3 player shield, which you can add on top of it, and you can design and build your own MP3 player. Okay. There's also color LCD displays, which gives you the same size, for example, some of the older cell phones, which was 128 by 128 characters big. Then there's, for example, also that Arduino motor shield, which allows you to operate DC motors. There's servo shields to operate servo motors. Now there's a number of these which you can have a look at. Now, one of the nice things about using the shields is that we can use some of the pre-written existing libraries. The thing with these libraries, it provides some extra functionality to us, which we can just use in our program, and we can implement very quickly. You don't have to go and rewrite it. A lot of times you can just extend it to some files. Now these files is written in C or C++, and a lot of times it's already then converted, and you also have the hex file to incorporate. Now, some of the things which you might be able to do with this is to control like an LED matrix, read temperature, control a motor. Okay. Then you actually don't need to write all the code to do that. You might just have one statement like read data, and you tell it what port you would like to read. And then it reads the port's data for you. But otherwise, there is initialization values, there's things which you might need to go through to do all of this. Now, there's a short list of possible libraries which has been included. Now, that include, for example, that EEPROM, reading and writing to permanent storage. There's a liquid crystal one. There's one for SD cards, reading and writing. Servo, keyboard or mouse. Okay. What can you use an Arduino for? What would you use it for? I've used an Arduino to build a fridge and a freezer controller to control the temperature, because what happened was Mr. Bosman had a fridge, and his fridge was hit by lightning. Just to replace the board of that fridge is 3,000 Rand. Yes. So I have built a small Arduino section from this, and it did not cost us 200 Rand. Now, how do you do that? What do we use? We use the small Arduino. We read the temperature sensors, which is already in the fridge. It was digital temperature sensors. So you read the values, and then based on the values, you just need to decide. You need to switch on the motor or not. How do you switch on the motor? Can you use the Arduino directly to switch on a motor? No. What electronic knowledge can you use to switch on a motor? You've been playing around with transistors, am I right? Okay, what is the purpose of a transistor? To act like a switch. Okay? If you apply a small voltage on the base, what happens between the emitter and the collector? It switches on and actually operates, and the current flows. Now, I used a transistor and a relay, because you can't directly connect a relay to Arduino. It doesn't provide enough amps from one of the pins to connectly power it. So that is what I've done with it. Now, what would you do with it? What small project would you play around with on something like this? Guys, we are going to be building an elevator system. You know that, by using something like an Arduino to design it, yes. Okay, so that is one of the things we should be focusing on. So the Arduino will be playing the main controller, and All of the logic and stuff will be going in there. What do we need to do from the Arduino? We're going to use the analog pins, for example, to read if a button was pressed. Okay. So you need to make some decision. Okay, what are we going to do from this button which was pressed? Okay. Should we, for example, turn on one of the output pins? Should we call, what should happen if the select floor button was pressed? Okay, so one of the things that might need, that means from this possibly we need to read the sensors to see, can we close this elevator door? Okay, so we look at some of that also. What else? We're going to need to at some point move the cage around. Okay, so you might incorporate one of the output pins to tell it go high, and then if you are high, we're going to start to move the motor. Okay. So those are some of the things that we will be looking to incorporate throughout the semester. Okay. Any questions? Okay. Guys, that is what we will be doing.